In the salt haze before stone learned its shape, when the planet was a grammar of heat and darkness, still finding its syntax, something older than memory moved through the molten spaces between what would become earth and sky. Not life, not yet, not form as we know it, but pattern, direction. A slow intelligence written in the way minerals cooled and crystallized, the way water gathered toward itself across a surface that had never known footsteps, had never known the weight of anything watching. The continents had not yet assembled their slow parade. The oceans held no reflected sky because atmosphere itself was still arriving, molecule by molecule, exhaled from stone. If there were civilizations then, they were civilizations of temperature and pressure, of chemical conversations held in the dark cathedral of a cooling world, empires of basalt rising from nothing, kingdoms of crystal forming their first geometries in silence, before the first shore, before the first horizon separated water from air, before anything that could turn and look back at its own becoming. And still the planet organized itself with something resembling memory, something resembling purpose, as if the future was already negotiating with the past, even when both were the same molten present moment, breathing. The question hangs in that pre-dawn stillness. What if consciousness is older than we think? What if the Earth was practicing civilization long before biology arrived to claim the concept? What if in those first billion years, when continents were only ideas scattered across a restless surface, something rose and fell and rose again, leaving no fossil, no foundation, only the faint organizational echo in the way matter preferred to arrange itself? We stand at the edge of that abyss now, 4.5 billion years later, asking questions the stone cannot answer, but somehow still remembers. Most geologists place the formation of Earth's first stable continental masses between roughly 4 billion and 2.5 billion years ago. The planet itself, condensed from the debris field of a young sun, began its existence approximately 4.6 billion years in the past. For the first several hundred million years, Earth was a molten sphere, its surface a magma ocean punctuated by the constant percussion of asteroid impacts. The moon-forming collision, that titanic meeting between the young Earth and a Mars-sized body researchers have named Theia, likely occurred around 4.5 billion years ago, reshaping both bodies into the configuration we know today. In those earliest ages, the concept of a continent, as we understand it, simply did not exist. The crust was thin, constantly recycled back into the mantle through processes that operated far more rapidly than modern plate tectonics. Any solid surface that formed would soon sink again, pulled down by its own density into the churning layers beneath. Scientists believe the first true continental crust began to stabilize as the planet slowly cooled, as lighter minerals separated from heavier ones through repeated cycles of melting and crystallization. Buoyant masses of granite and related rocks accumulated, too light to subduct, too persistent to dissolve. Evidence suggests that by 3.8 to 3.5 billion years ago, small protocontinental fragments existed, scattered islands of stability in a global ocean. These were not the familiar landmasses we see on modern maps. They were smaller, isolated, drifting on a more vigorous convection system that rearranged the surface with restless energy. The atmosphere above them held no oxygen, only methane, ammonia, carbon dioxide, and water vapor. The sky would have been a strange color, perhaps orange or brown, filtered through haze that captured and scattered light in unfamiliar ways. The first supercontinent, which some researchers call Valbara, may have assembled around 3.6 to 2.8 billion years ago, though the evidence remains fragmentary and debated. Others point to or Kenorland as the earliest stable assemblies. What seems clear is that by 2.5 billion years ago, significant continental masses existed, even if they bore no resemblance to the continents we walk upon today. They drifted, collided, fragmented, and reassembled in cycles that stretched across hundreds of millions of years. During all of this, the magma ocean epochs, the protocontinental formation, the early supercontinent assembly, Earth was utterly lifeless in the way we typically understand life. Perhaps the simplest bacteria-like organisms had emerged by 3.8 billion years ago, though even this is uncertain. Most estimates place the origin of life somewhere between 4.1 and 3.5 billion years before the present. But complex life, multicellular organisms, anything resembling the diversity we associate with biology, would not arrive for billions of years more. Animals did not emerge until roughly 600 million years ago. Land plants colonized the continents only about 450 million years in the past, which means that for perhaps 3 billion years or more, the continents assembled and dispersed while utterly empty of anything we would recognize as civilization. No cities, no tools, no language, only chemistry and geology performing their slow negotiations in silence. Geologic records show that these early landmasses recorded the planet's story in layers of stone, sediments laid down in ancient seas, volcanic deposits marking moments of upheaval, impact craters documenting the bombardment that continued for hundreds of millions of years. The oldest minerals we have found, tiny zircon crystals from Western Australia, date back 4.4 billion years and carry within their structure traces of water, suggesting the first oceans may have condensed even earlier than once thought. The planet was learning its own physics during those ages, learning how heat moves through rock, how water shapes continents, how minerals transform under pressure. A curriculum of thermodynamics and chemistry, written slowly in the deep grammar of matter itself. And yet, embedded in this history is a peculiar pattern, a tendency toward increasing complexity, increasing organization, even in the absence of life. The question that haunts the edges of this story begins to take shape in that observation. What kind of order existed before biology claimed the concept? Most planetary scientists would say that the organization we observe in Earth's early geological processes arose from physics alone. Thermodynamic gradients, gravitational sorting, chemical equilibrium seeking its lowest energy states. There is no need to invoke anything beyond material causation. The patterns of continental assembly, the layering of minerals, the cycling of water and rock through the proto-tectonic system, all of this follows from the fundamental properties of matter and energy. And yet, some researchers studying complex systems have noted that self-organization appears at every scale where energy flows through matter. Crystals organize themselves into geometric lattices without instruction. Convection cells form spontaneous patterns in heated fluids. Even the distribution of craters on the ancient lunar highlands shows statistical regularities that suggest underlying organizational principles. The universe, it seems, has always preferred pattern to randomness, structure to chaos, even when no consciousness directs the preference. Perhaps the earliest Earth, in its pre-biological epochs, was already experimenting with forms of order that we lack the vocabulary to describe. Not life, but not merely random either. Information processing of a kind, the way certain mineral arrangements catalyzed specific chemical reactions, the way temperature gradients drove circulation patterns that in turn shaped where new crust formed and where old crust descended. Feedback loops without nervous systems, memory encoded in crystal structures rather than neural networks. Beyond the record's edge, where data dissolves into speculation, we might imagine those first proto-continents as something more than passive rafts of stone. What if they functioned as massive chemical computers, their surfaces hosting reactions that could store and transmit information across geological timescales? Some studies propose that certain clay minerals can act as templates for complex organic molecules, essentially preserving and replicating molecular patterns. If this occurred on the pre-biological Earth, scattered across those ancient landmasses, could we think of it as a form of proto-cultural transmission? Stone teaching stone, what configurations of matter were most stable, most persistent? The question fractures into stranger territories the longer we hold it. If we define civilization as the capacity to store information, to build upon accumulated patterns, to create structures that outlast the individual components that built them, then perhaps the first civilizations were civilizations of mineral and water, constructing their legacies in chemical gradients and crystalline architectures. They rose in the sense that complexity accumulated in certain configurations. They fell in the sense that every stable system eventually encounters conditions that force its reorganization. They left no ruins we would recognize, because their cities were written in arrangements of silicon and oxygen, their monuments recorded in the ratios of isotopes locked within ancient rocks. The volcanic arcs that formed along the edges of those early proto-continents might have served as sites of intense chemical processing, not production in any economic sense, but transformation. Seawater circulated through hot rocks, emerged enriched with minerals, deposited those minerals in layered sequences that recorded the history of thermal and chemical change. Each hydrothermal system was unique, shaped by the specific geology of its location, creating regional variations in mineral assemblage. Were these variations the equivalent of different cultural traditions? Different solutions to the same thermodynamic problems? It may be more honest to imagine these processes as neither alive nor dead, neither conscious nor unconscious, but occupying some category for which we have no adequate language. The Earth, in its first billion years, was engaged in a kind of learning, not cognitive learning, but the kind of learning that happens when any complex system responds to its environment, when feedback shapes future behavior, when pattern begets pattern. Mountains rose and eroded, each cycle refining the distribution of elements. Ocean chemistry shifted as new gases bubbled up from the mantle, as impacts delivered volatile compounds from space. The whole system was in conversation with itself, adjusting, experimenting, finding stable configurations through trial and iteration. Some researchers propose that the origin of life itself may have been facilitated by these pre-biological organizational patterns, that the chemistry of early Earth had already assembled the building blocks and reaction pathways that biology would later co-opt. In this view, life did not emerge from chaos, but from an already semi-ordered system, a planet that had spent hundreds of millions of years preparing the ground. The first cells would have inherited metabolic strategies that rocks had been using for eons, how to move electrons from one molecule to another, how to harness chemical gradients for energy, how to build complex structures from simple parts. Meanwhile, in the stone, beneath the restless oceans, another kind of memory was being written. Every tectonic event, every meteorite impact, every shift in ocean chemistry left its signature in the rocks that would eventually become the oldest parts of our continents. These cratons, the stable cores of modern land masses, still carry within them the encrypted history of those first billions of years. Seismic studies reveal that the deep continental roots extend hundreds of kilometers down, composed of ancient mantle material that has been attached to the underside of the crust since the Archean eon. They are keels, stabilizing the lighter crustal rafts above them, and they are archives, preserving mineral assemblages that formed under conditions no longer present anywhere on Earth's surface. When geologists drill into these ancient formations and extract core samples, they are, in a sense, excavating the ruins of those pre-biological arrangements. Not ruins of civilizations as we use the term, but ruins nonetheless, remnants of organizational states that existed and then transformed, leaving only their compressed and altered remains. The greenstone belts that snake through the oldest cratons contain rocks that were once ocean floor, volcanic islands, sedimentary basins, whole geological provinces now squeezed and folded and metamorphosed beyond their original form. Reading them requires an act of translation, deciphering what each mineral transformation implies about pressure, temperature, time. And somewhere within the silence of those transformations lies a truth we can only circle without landing, that the planet was doing something during those first billions of years, something that looks from our perspective like preparation, like rehearsal, like the slow construction of the conditions under which consciousness would eventually become possible. Perhaps the ancient Earth was not waiting for life to arrive and give it meaning. Perhaps it was already meaningful in its own terms, a vast chemical symphony playing out themes of oxidation and reduction, dissolution and precipitation, heat flow and tectonic motion. The continents that had not yet formed were nonetheless implicit in the physics of the system, waiting in the mathematics of density and buoyancy, ready to emerge when temperature and composition reached the right threshold. The civilizations that rose and vanished before the continents took shape were not civilizations of minds or hands, but civilizations of process, intricate, self-sustaining, evolving patterns of matter and energy that built upon themselves, that left records, that influenced what came after. They spoke in chemical dialects that predated language. They built monuments that dissolved back into the mantle. They measured time in the slow accumulation of mineral layers, in the gradual cooling of an iron core, in the number of times ocean water could cycle through mid-ocean ridges that had not yet formed their modern configuration. Over ages, the organizational capacity of the planet grew more sophisticated. The first atmospheric oxygen, produced by photosynthetic bacteria around 2.4 billion years ago during the Great Oxidation Event, fundamentally restructured the chemistry available to the Earth system. New minerals became possible, iron oxides, sulfates, carbonates, that had been unstable in the reducing atmosphere of the Archean. The continental crust thickened as new mechanisms of crustal growth emerged. Supercontinents assembled and broke apart in grand cycles, each iteration slightly different from the last, as if the planet were learning optimal configurations through repeated experimentation. It was not an ending, only a pause. Each tectonic cycle ended in dispersal, but the dispersal carried forward the information encoded in the previous assembly. Each subduction zone consumed old ocean floor, but in doing so transferred volatile compounds back into the mantle, enriching the sources that would feed the next generation of volcanic arcs. Every process was both destruction and preparation, erasure and memory. The planet had become a system capable of preserving its own history even as it continuously rewrote the surface. The ancient zircons survived because they were chemically stable, physically durable, and small enough to be carried through multiple cycles of erosion and sedimentation without being destroyed. They are the sole witnesses to Earth's first 500 million years, tiny time capsules that persisted through everything that came after. In a sense, they are the civilization's only remaining artifacts, not built with intention, but preserved by the same forces that built without intention. And in the quiet between epochs, the question transforms from whether civilizations existed before continents to what we mean when we use the word civilization at all. If it requires consciousness, then the answer is no. The early Earth was empty of minds. If it requires merely complexity, persistence, and the capacity to shape future conditions, then perhaps the answer shifts toward maybe. If civilization is ultimately just matter organizing itself in increasingly unlikely configurations, maintaining those configurations through energy flow and propagating patterns across time, then the boundary between geology and culture becomes harder to define. The light pauses. When stone forgets its shape, does it still remember heat? When ocean water, cycled 10,000 times through hydrothermal vents, finally locks itself into a mineral lattice, does some trace remain of all the places it has been? The past is never wholly past. Physics does not permit it. Every current state of a system contains within it the constraints imposed by every prior state. History becomes structure. Time becomes chemistry. We live now on continents that are composites, pieces of ancient cratons sutured together with younger material, each province telling a different story about when and how it formed. The ground beneath our feet is a palimpsest, written and rewritten, the oldest texts still visible beneath the newer inscriptions. Walking across a landscape, we walk across time itself, though our single lifetimes give us no sense of the immensity beneath each step. 4 billion years ago, give or take a few hundred million, the first stable land masses emerged from a global ocean. They were smaller than modern continents, perhaps more accurately called continental nuclei or protocratons, but they persisted. They survived the tectonic recycling that had claimed every previous attempt at stable crust. And in surviving, they changed the system. They altered ocean circulation patterns, created shallow water environments where wave action and sunlight could interact differently, provided surfaces where chemical gradients could concentrate. 3 billion years ago, small continents drifted across a planetary surface that looked nothing like our own. 2 billion years ago, continents collided and assembled into supercontinental masses, then rifted apart again. 1 billion years ago, the supercontinent Rodinia began its slow aggregation, drawing together fragments from across the globe. Each cycle of assembly and dispersal took hundreds of millions of years, durations that make the entire span of human history seem like a single breath. And through all of this, the planet was never static, never finished. It kept experimenting with configurations of matter and energy, kept testing different arrangements, kept building complexity upon complexity. Not with purpose, perhaps, but with the same inevitability that water flows downhill, that entropy increases, that energy disperses according to the gradients available to it. The anthropologist in us wants to see intention where there may be only consequence. The poet in us wants to see memory where there may be only residue. But the distinction may matter less than we think. Memory is residue. In brains, memory is the residue of neural activity, patterns of connection strengthened by repetition. In stone, memory is the residue of thermal and chemical events, patterns of mineral arrangement that preserve traces of the conditions under which they formed. Different substrates, similar principles. If the Earth remembers, it remembers in the language of isotopes and crystal lattices, in the orientation of magnetic domains frozen into cooling basalt, in the ratios of elements that speak of ancient atmospheric compositions. It remembers the way any complex system remembers, by carrying forward the consequences of its history into its current state, by being shaped by everything that came before. And if it dreamed, during those first billions of years before consciousness arrived to claim the concept of dreaming, it dreamed in the slow permutations of possible configurations. Continental arrangements tried and discarded, ocean chemistries explored and superseded, atmospheric compositions that gave way to others as the system evolved. Not dreams of narrative or imagery, but dreams of structure, of relationship, of stable patterns emerging from flux. We are, all of us, made of the same elements that cycled through those early systems. The calcium in our bones was forged in stars that died before the sun was born, then incorporated into the Earth's original inventory of elements, then cycled through ocean and crust and mantle for billions of years before briefly taking the form of skeleton. The iron in our blood traces a similar journey: stellar nucleosynthesis, planetary accretion, geological processing, biological co-option. We are not separate from the deep history of matter. We are its latest expression, its most recent experiment in self-organization. Oceans rose, continents wandered, time kept breathing. The pace of change was so slow that from any single vantage point, it would have appeared frozen, eternal, changeless. Only across millions of years does the motion become visible. Only from the perspective of deep time does the restlessness resolve into pattern. Mountains that seem permanent are merely slow waves in the crustal fabric. Coastlines that define our maps are temporary negotiations between land and sea. The very distribution of continents and oceans is contingent, one configuration among many possible, held in place only by the current momentum of the system. And yet within that contingency, within that flux, something accumulates. Complexity builds upon complexity. The early Earth, with its global magma ocean, gave way to an Earth with protocontinents. That gave way to an Earth with true continental masses. That gave way to an Earth with supercontinents and deep ocean basins. That gave way to an Earth with oxygen in its atmosphere, which gave way to an Earth with complex life, which gave way to an Earth with us, asking questions about its own history. Each stage was improbable until it happened, then it became the foundation for the next stage. Each transition required specific conditions to align: the right temperature, the right chemistry, the right tectonic configuration. Luck played a role, if luck is the right word, for the intersection of physical law and initial conditions and chaotic dynamics. But perhaps luck is too flimsy a concept for something that took billions of years to unfold. Perhaps we need a different word for inevitability, working itself out across deep time. The civilizations that were not civilizations, the patterns that were not quite life, the memory that was not quite consciousness, all of it folded into the next iteration, contributed to the conditions that made the next step possible. Nothing was wasted, nothing was truly lost. Even the subducted ocean crust, dragged down into the mantle and melted and dispersed, contributed volatile elements back into the convection system, enriching the sources that would later supply volcanic arcs with the gases and fluids necessary for ore formation and crustal growth. The planet was building toward us, not with intention, but with the same apparent directionality that entropy builds toward equilibrium. We are not the goal, there is no goal, but we are the current high water mark of the complexity the Earth system has managed to generate, the most intricate expression yet of matter organizing itself to process information and reflect upon its own existence. Time exhales. Return now to the image we began with, the salt haze before continents, the heat grammar of a world still learning its own language. The question we brought has dissolved into something larger and quieter, no longer a question at all, but a kind of listening. Did civilizations rise and vanish before the continents formed? The answer depends on what we mean by civilization, what we mean by rise, what we mean by vanish. If we mean creatures building cities, then no, biology had not yet arrived. If we mean complex systems maintaining far from equilibrium states through energy flow, creating order and memory and persistent structures, then yes, the Earth was already engaged in that work, already experimenting with stability and change, already recording its history in the medium of stone. The continents did not emerge into emptiness. They emerged into a system already rich with pattern, already engaged in the project of self-organization. They inherited the tectonic mechanisms that had been refining themselves for hundreds of millions of years. They incorporated the chemical wisdom that early ocean crust interactions had discovered. They built upon foundations that had been laid invisibly, incrementally, through processes too slow and vast to observe from any single point in space or time. And they drift still, these continents, moving at the pace of growing fingernails, carrying us with them across a planetary surface that will look entirely different in another 100 million years. The Pacific will grow or shrink. The Atlantic will widen or close. New supercontinents will assemble. The Himalayas will erode back into the sea. Everything we think of as permanent geography is temporary configuration, frozen motion, stone pretending to be still. Dusk settles over the ledger of stone. Somewhere beneath our feet, the mantle continues its convection, hot rock rising in some places, cooling rock descending in others, the same cycle that began when the planet first solidified and will continue until the core itself freezes billions of years from now. Somewhere at the mid-ocean ridges, new crust is being born, magma cooling into fresh basalt, minerals crystallizing in patterns that reflect the current state of seawater chemistry and temperature. Somewhere at subduction zones, old crust is dying, dragged down into the furnace, melted, dispersed. Its elements returned to the great reservoir for future use. The planet breathes this way, has always breathed this way. We have simply learned to read the rhythm. In the darkness before dawn, before the first continent knew its own outline, before water reflected the first sky, something stirred. Not life, not mind, but the restless capacity of matter to organize itself, to build, to remember, to dream in the slow language of chemistry and heat. Those early patterns are gone now, transformed beyond recognition by billions of years of subsequent activity. And yet they persist, encoded in the deep structure of the cratons, in the fundamental architecture of plate tectonics, in the fact that we stand here at all, able to ask about them. We are the Earth interrogating its own past. We are the planet's memory looking backward at itself. The civilizations of mineral and water, if they existed, have become us, not through any lineage we can trace, but through the accumulation of complexity they made possible. Every step toward greater organization, toward more sophisticated information processing, toward more persistent structures, was a step toward the emergence of consciousness and the questions consciousness brings. The final darkness gathers. And the question we carried here, the question about civilizations before continents, releases us from the need to answer it. Perhaps the point was never to resolve the paradox, but to sit with it, to feel the vertigo of deep time, to recognize that our definitions are always too small for the vastness we're trying to contain. The Earth in its first billions of years was doing something we lack the language for, something between geology and memory, between chemistry and culture. It keeps doing that something now, stone by stone, breath by breath, age by age. The planet turns, continues. So do we.